Hello and welcome to this video from Learning Dojo. My name is Gillian Hush and I write the Learning Dojo resources for teachers and students of Physics A-Level. In this video, I'm going to suggest how to introduce and frame the practical skills requirements of the current A-Level spec so that they make a genuine contribution to your students' understanding and abilities. And at this point, I'm going to take a moment to acknowledge that practical skills, as they appear in our current specifications, can feel like an unwieldy and rather arbitrary set of techniques that achieves little apart from making our students miserable. So how do we convince our students, and perhaps ourselves, that they do in fact add something important? I'm going to talk about demonstrating to students the importance of method and the importance of uncertainties. And what we really mean here is convincing them that these things matter in the real world. They're not just answers to exam questions. So method first. For the very first lesson of the A-Level, we have our students do the Alien Mass Challenge. The Alien Mass is just a piece of plasticine, although in Googling pictures for this presentation, I realised I've been missing a trick all these years, so here's what your alien masses could look like. Working in groups, students have to build an instrument to measure the mass of a small object. What our students do is clamp a hacksaw blade to the desk and measure its deflection when known masses are suspended from the end. They are told they have to plot a graph. When they're ready, they request the alien mass from us and make their deflection measurements and then use their graphs to convert these to mass measurements. It's up to you how much of a challenge you want to make it and whether you want to allow for other solutions. We then ceremoniously weigh the alien and declare the group whose mass measurement is closest the winner. And at this point, you can have a discussion about what the winning group did differently. So did they have more points on their graph? Were they more spread out? Did they do repeats? Did they have more scatter on their graph? Why might that have been? Did they clamp their ruler? Did they wait longer for the mass to stop moving? Did they bend their knees and look at eye level when they made their measurements? All of the things they actually did during their practical. And so, because they can see that some groups have got closer to the correct mass than others, they can see that how the practicals were carried out by the different groups has made a difference to the quality of data that was gathered. So I think it shows in a convincing way that the decisions you make while carrying out a practical do have a significant impact on the data that you gather and how useful that data is. This practical also allows you, at the very beginning of the A-Level, to bring up the ideas of the experimental value of a quantity compared to the true value or accepted value of that quantity, the error as the difference between these two, and accuracy as a measure of how large the error is. And of course, the practical, in your discussion, you've been talking about factors that affected the size of the errors in the practical. While students are working, you can of course wander around and talk to them about a whole host of other relevant practical skills questions, some of which are listed here. It's also a fun lesson that gets students talking to each other, and I think that since starting the A-Level with this lesson, our students are more independent in their practical work, and they understand that the outcome of their practical is something they have control over. So that's how I would make the point that experimental design matters. Now for why uncertainties matter. Now, we all obviously know that without uncertainties, you can't decide whether your results support a hypothesis or not. But to frame it in a more concrete and very familiar way, let's imagine that we have a student who gets a graph like this for the Hooke's Law practical. Now, our students all know that the line should be a straight line through the origin, and so when it isn't, they start to ask questions like, why isn't it? Are the third and fourth points anomalies, or maybe the other 3 points are all anomalies? What should I write in my conclusion? Is Hooke's Law only right sometimes? Now, without an understanding of uncertainties, the students don't have a way to answer these questions, and you see it in their eyes that they really don't know what the answer to these questions are, and they start writing things like this. Hooke's Law states that f is directly proportional to x. My results don't show this because I didn't do the practical carefully enough. In other words, they are simply writing down what they know the right answer should be and ignoring the evidence that they have just collected. Now, quite apart from the fact that we don't want to be raising adults that ignore the evidence in front of their eyes and simply repeat what they think the answer should be, it's quite possible that the students, in fact probable, that the students' results don't include any anomalies and in fact do support Hooke's law. So the student is losing faith in their own practical ability unnecessarily. What the student needs to do is estimate the absolute uncertainties of their measurements and plot these on the graph as error bars. Once they do that, they can see that they can draw a straight line of best fit through all the points, so none of these points are anomalies. They can then also draw the worst acceptable lines through the error bars, and this shows them the range of positions that their line of best fit could be in. At this point, if they could get a straight line between the worst lines that went through the origin, they could say that's okay, it's only the random error in my practical that has meant my line does not go through the origin, and in fact my results do support Hooke's law. However, for this student they can't say that, and their results instead suggest they have a systematic error. Looking at the graph, that systematic error is, if we project the line, probably about a centimetre or so, which is coincidentally the size of the ring at the end of a spring. And so almost certainly what this student has done is clamp the ruler with the 0 mark at the bottom of the loop, but then they've measured the extension to the bottom of the coiled spring section at the top of the loop, making all their extension measurements about 1 centimetre too small. And so once students have reached this level of understanding, they can answer all these questions and it doesn't feel like a mystery anymore, and practicals don't feel like magic anymore. And the uncertainties become a really powerful diagnostic tool. So take, for example, this resistivity practical graph I drew the other day, and you can see that on here I've got a systematic error. It's either an error of about 8 centimetres on the length of the wire, or it's an error of about 0.35 ohms. 8 centimetres on the wire is not a realistic error. I won't have been out by that much. But the 0.35 ohms, that is probably, if you look up the resistance of a crocodile clip, it's around about half an ohm. So it's probably the resistance of the crocodile clip. And so now I have the opportunity to go back to my practical and try it again without the crocodile clip and see if it removes the systematic error. And of course this doesn't only apply to graphs. Suppose we were testing the hypothesis that the speed of sound in air is 343 metres per second. We could carry out a standing wave practical, and if we have the value shown here, this, from estimating the uncertainties, this shows that random error alone is enough to explain why we did not get 343, and so our results do support the hypothesis, although not as strongly as they might. And we can go back to try to improve this practical, looking for ways to reduce random error. We don't need to look for a systematic error. Now obviously you need to build students up to the point where they can analyse their data in this way, and you need to build in succession all of these ideas. And so this is where I introduce them roughly throughout the A-level, and you can see most of it's done by the end of the lower sixth. And I think the final important thing to say is that you need to choose very carefully the practicals that you use to introduce some of these ideas. For many practicals, error bars will be either enormous or so small they don't show up. And so it's important that you have tested the practical and you know it's going to give sensible results the first time that students meet that technique. And so this is my plug. The new set of worksheets coming out very shortly, within the next couple of weeks, is just that. It's a list of practicals, activity sheets, teacher sheets, sample results that show you where you can introduce these each skill in a way that's going to work in a nice controlled manner and give sensible results. And also there's this document which maps out where the skills are being covered throughout these practicals. And so just to return to the question there, why do uncertainties matter? This is your chance for a noble moment. The scientific method can't function without them because the real world doesn't give us perfect results that all lie perfectly along the true line of best fit. And so if we are ever to interpret real world results, we have to have a good, strong grasp of uncertainties. And if you're an NQT teacher and that's on your to-do list, please subscribe because more videos will be following shortly on how to do each of the individual techniques.